Welcome back. Before proceeding to the next topic on capillarity, we stopped with this in the previous lecture, and I would like to focus or direct your attention to the first statement of the problem, which is given as the pressure outside the droplet is 10.32 Newton per centimeter squared atmospheric pressure. Okay, so what is given in the problem is the atmospheric pressure is mentioned as 10.32 Newton per centimeter squared. So if we convert this to Newton per meter squared, it has to be multiplied by 10 to the power 4. So that would be 3200 Newton per meter squared. Okay, so what we require is the pressure within the droplet. Okay, so the pressure within the droplet that is supposed to be equal to the pressure which we have found out plus the pressure which is the atmospheric pressure. So 7250 plus 103200. So that makes this 11, 1,10,450 Newton per meter squared. Or if you need to write this in terms of Newton per centimeter squared, it should be 11.045 Newton per centimeter squared, or it can be written as 1,10,450 Newton per meter squared. Okay, since they have specifically asked that for the pressure inside the droplet, it has to be added in terms with reference to your atmospheric pressure. Okay. Let's move on to the next topic, which is capillarity. So it is defined as the phenomena of rise or fall of a liquid surface in a small tube relative to the adjacent general level of fluid when the tube is held vertically in the liquid. So now look at this particular picture. I have a vessel of a liquid, say, let's say this is a vessel of liquid with water. Okay, and the level of the liquid is that is what is shown to us in the problem. Now, what I'm doing is I'm going to inside a tube which is open at both the ends. It is open at the bottom end and it is open at the top end, and I'm going to insert it into this vessel. And what I find is that is a little bit higher than the level of the liquid in the vessel. So it is h times, or the height of this particular fluid, which is higher than the liquid in the vessel, is denoted by h. And that is what we call as capillary rise. So this h, let's say this is the amount by which, that is the rise of the fluid in the tube uh, inside this particular tube. And you can see that there is this surface tension which is acting on the surface. And we know that it is going to act throughout the circumference. So it is something like a test tube which is open on both the ends. So you are going to have this particular dip throughout the circumference of the fluid. So what you have here is the surface tension force that is acting on the layer, the free surface of this particular liquid, or the liquid that is in contact with the surface of the tube. Okay, so that is one force that is acting in the upward direction. And what is the force that is counteracting this one? That is going to be the weight of the liquid, which is at a height h. And this height h is the level of the liquid above the level of the liquid in the vessel. So it is the weight of the fluid that is going to be that is counteracting the surface tension force. So we have to write, say, the weight of liquid in the tube, that is going to be equal to the surface tension force acting along the circumference of the tube. So if we say the diameter of the tube is, say the diameter of the tube is denoted by D, so the surface tension, it is going to be sigma times pi D. But what we need to look at is there is, because of this meniscus that we have, so there is going to be an angle of inclination with reference to this. So we are talking about the downward force of weight and the upward force. So we are supposed to take the vertical component. So the vertical component of this particular force with reference to sigma. So I need to find out the value of this force over here. And I have got sigma acting like this. And this would be my horizontal component in this direction. And this is my is going to be F by sigma, or F is equal to sigma cos theta. Okay, so I just don't have the sigma. I also have this cos theta because that is what the vertical component of this force is. So what I have is force acting along the circumference of the tube. Okay. Then we have, so since we are taking the vertical component, let's acting along the surface of the tube. That would be a better word rather than saying it as the circumference. So acting along the surface of the tube. So what is the weight of the liquid in the tube? That is usually denoted by mass times acceleration due to gravity. And what is this mass? That is going to be the density of the fluid multiplied by the volume of the fluid. So that is the volume of the fluid in this particular pipe. So that is h multiplied by pi by 4 d squared. So this would give me the volume. So pi by 4 d squared into h would give me the volume. So rho into v will give me mass, and this has to be multiplied by g. So now I can cancel out some of the common terms on both sides. I can cancel out one of this d over here, and I can cancel out this pi term. So what is left out is h is 4 sigma cos theta divided by rho g times d. Am I right? So this 4 goes over here, 4 sigma cos theta, and what is left out is this rho, one of this d, and g. Okay, so now, so if we look at the previous slide, so this is what we mentioned as the phenomena of rise or fall. So the rise of the liquid surface, that is going to be capillary rise, and some of the fluids, if you are going to dip that particular tube, you are not going to have a rise, rather you are going to have a depression. You are going to have a fall of the liquid surface, and that is called as capillary depression. So this capillarity, it depends on the specific weight of the liquid, the diameter of the tube, and the surface tension of the liquid. Okay, so now we have already seen what this capillary rise is. Let us also focus on what capillary depression is. Okay, so let me have the fluid as mercury. So now I have a vessel of mercury, and just like in the previous case, I'm going to insert a tube that is open on both the ends into this mercury, into this vessel that is filled with mercury. And you will see that the mercury has not risen in the tube. Rather, the level of the mercury in the tube is lesser than the level of the mercury in this particular vessel. And it is lower by a height h. So this fall in the level of the fluid inside the tube is what we call as capillary depression or capillary fall. Okay, so the capillary fall is denoted by the term H. So H is the fall in in the tube. which we call as capillary depression or capillary fall. Okay. Acting in the downward direction. In the previous case, it was acting in the upward direction. But once again, it is going to be acting throughout the surface of your tube. And so we can say that you have the surface tension force acting along the surface of tube. And this should be equal to, in the previous case, you had the surface tension force acting upwards. Now your surface tension force is acting in the downward direction. So this has to be counteracted by an upward force. And you can see that this is the intensity of pressure. And what is this intensity of pressure? This is nothing but the hydrostatic force, which we'll be learning a little bit later. Probably in the next video lecture, we will look at that. So this is the hydrostatic force, which is acting in the upward direction. And so this is the reference to the pressure P. And so you are supposed to multiply it with the cross-sectional area. So that is going to be P times pi by 4 d squared. And this P with the reference to the height h can be written as rho g h. And this is what we are calling what it is all about. So for the time being, take this as speed is rho g h times, rho g h. And then on the left-hand side, we need to have the surface tension force. And once again, you have this angle of inclination. So this is also going to be sigma times pi d cos theta. Okay, and now I can cancel out the common terms on both sides. I will be able to cancel out one of this pi and one of this d. And so what is left out is again 4 sigma cos theta divided by rho GT, the same expression that we get. Okay. The one thing which you should understand here is if the fluid is going to be mercury, this theta is somewhere between 125 degrees to 130 or 135 degrees. It is usually 130 degrees. If the value of theta is not mentioned to you in the problem and they have mentioned that the fluid that is used is mercury, you can take it as 130. This is a common expression that you have. And so if the fluid is, so this theta value is for, but if the liquid is water, you can take the value of theta as 0 degrees. So cos theta is going to be, cos 0 is going to be 1. And then you will have simply 4 sigma divided by rho gt. And this expression is applicable only that is when your liquid is water. Okay, so that is your capillarity, the rise or fall in the tube when it is immersed in a vessel of the liquid. That rise or fall in the tube is what we call as the capillarity. Okay, let's solve an example over here. Calculate the capillary rise in a glass tube of 2.5 mm diameter. So they have said that the diameter is 2.5 mm for the tube. So that is going to be 0.0025 meters when immersed in water. So the first subdivision, we are having it as water. And for water, they have said that the surface tension is going to be 0.0725 Newton per meter. And the second subdivision is going to be mercury. And they have said that for this, the surface tension is going to be 0.52 Newton per meter. And the specific gravity of mercury is given as 13.6. So density of mercury is going to be 13,600 kilogram per meter cube. We have already seen how to get this density from the specific gravity value in one of our previous lecture, the angle of contact is going to be 130 degrees. Okay, so for water, default theta is going to be 0 degrees and density of water is 1000. Okay, so what they want us to find out. So it is 4 sigma cos theta by rho GD. Cos theta, we are going to have 0. So cos 0 is 1. So it is simply 4 sigma by rho GD. So 4 times 0.0725 divided by 1000 multiplied by 0025. So this should give us what is the rise in the level of that is the capillary rise. Similarly, for mercury over here, we need to write this as, let's change the color. So it is 4 sigma cos theta by rho GD. So it is 4 times 0.52 into cos 130 divided by rho is 13,600. And this is 9.81 into 0.00, sorry about that, 0.0025. So if we use the calculator for both these cases, let's see what we get. So let's use the calculator. Four into 0.0725 whole divided by 1000 divided by 9.81 divided by 0.0025. And so that gives us 0.0118. So 0.118 mm. So that is what we get in case of water. In case of mercury, let's see what we get. 4 into 0.52. So we have got this 130 divided by 13,600 into 9.81 into 0.0025. So that is minus 0.004. So that is minus 0.004 meters. So that is 4 mm. And the minus sign indicates that it is a fall. There is a drop in the level of the fluid. Okay, so that is what we get as a result in case of water as well as in case of mercury. Okay. The next question is the capillary rise in the glass tube is not to exceed 0.2 mm. So now they have said that the value of H is 0.2 mm. So which means that is 0.0002 meters. Determine its maximum size. So then now they want us to find out the value of D. They have said that it is 1. And they have said that the surface tension for water is 0.0725 Newton per meter. So what we know is H is 4 sigma by rho GD. And now they want by rho GH. So it is 4 into 0.0725 whole divided by 1000 into 9.81 into H is 0.0002. So let's see. Let's use the calculator and see what we get. 0.0725 divided by 1000 multiplied by 9.81 and finally we get 0.14 8 meters, which is approximately 148 mm. So that is what we get as a result. Okay, that is the diameter of the pipe that is used. So that's it for today's lecture, and we'll meet again in the next video lecture for fluid statics. Thank you.